Hello, welcome back to chemistry class. Today's session, the learning objective is sulfonation, electrophilic substitutions in benzene. And electrophilic substitution in benzene, I've explained you about the nitration, chlorination. Electrophilic aromatic substitution reactions. In substitution reactions, we have nucleophilic, electrophilic, free radical. One, the substitution is replacement of weaker or a stronger, weaker atom or a group by a stronger atom or a group is called substitution. There we have seen three types of substitutions. One is electrophilic substitution, nucleophilic substitution, free radical substitution. Free radical substitution reactions. So, nucleophilic substitutions are observed in nucleophilic substitution reactions are observed in, you can see the halogen compounds. Free radical substitutions are observed in, you can see, they are observed in the alkanes substitution reactions, halogenation of methane, chlorination of methane, ethane. The halogenation of the alkanes can give the free radical substitution reactions. And the next one is the electrophilic substitutions. Electrophilic substitution reactions, we are having the common mechanism, that is for benzene we have seen. Benzene and other organic compounds. So benzene, it is very rich in the pi electron system. It is having pi electrons and it can easily undergo the substitutions. And why this electrophilic substitution takes place is aromatic hydrocarbons, the general formula, the benzene, it is C6H6. And since the saturated compounds, carbon 6 and 14, the benzene expected to be unsaturated hydrocarbon, which can give the different reactions, that is, chlorobenzene can be formed, benzene trioxanide can be formed, catalytic hydrogenation can be formed. So this type of reactions are undergone by the benzene. And most probable reactions and the most occurring reactions for the benzene are the electrophilic substitutions. Benzene are generally it is the aromatic compound. The Huckel's rule, it follows the Huckel's rule. Benzene, it is aromatic compounds, and mostly benzene, it is expected for substitution rather than the addition reactions. Although they possess the double bond, they don't undergo the additions, but they undergo electrophilic substitutions like nitration, halogenation, sulfonation, Friedel-Crafts reactions. So, the aromatic substitutions mostly occur in benzene. The replacement of an atom, generally hydrogen or a group attached to the carbon of the benzene ring by the another group is known as aromatic substitution. So, electrophilic substitutions, SE, it involves the attack of the electrophile and electron seeking reagent. Nucleophilic substitutions involve attack of the nucleophile or electron emitting reagent. The free radical substitution, free radical attacks. Okay. As why these aromatic undergo the electrophilic substitutions? Why mostly the aromatic compounds, that is benzene, undergo electrophilic substitutions? See, after giving this introduction, I'm going to explain you about sulfonation, Friedel-Crafts alkylation, and acylation. Due to presence of pi electron cloud above and below the plane of the benzene, the ring serves as the source of the electrons and is easily attacked by the electrophiles. electron loving reagents. Hence, the electrophilic substitutions are characteristic reactions of the aromatic compounds. The electrophilic, yeah, the experimental evidences indicate that the electrophilic aromatic substitution reactions proceed by common mechanism, and they'll follow the mechanism in general and apply for the specific substitution reactions like nitration, hallucination. Nitration hallucination is discussed in previous class. Now comes our actual topic, that is sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. Electrophilic substitutions, aromatic substitution reactions, are believed to be SC2 reactions. They occur in three steps: generation of the electrophile, generation of the electrophile. The second one is formation of the carbonium ion, and the third one is formation, the stabilization of the carbonium ion, and the fourth one is formation of the product. So, first step, attacking of the attacking of the electrophile is generated from the reagent. In the second step, electrophile approaches benzene, undergoes electromeric effect. Your curved arrows, you can see, and it results one carbon of the benzene gets positive charge and the other one gets the negative charge. The electrophile then attacks to the negative center, resulting in the formation of intermediate aronium or the carbonium cation sigma complex or pentadienyl cation complex. The carbonium ion 1, it is stabilized by resonance structures 1, 2, and 3. And the resonance hybrid can be represented by structure 4. So 4 different structures, and thus the positive charge of the intermediate carbonium ion can be confined to carbon, but it is dispersed over the entire molecule, especially on the ortho and para positions with respect to carbon, carrying the attacking reagent. Since formation of the intermediate carbonium ion is slow step, it constitutes the rate determining step of the complete reaction. The formation of the carbonium ion, it is the slow step, and therefore that is the rate determining step for this whole step. And finally, there is the formation of the product. The reaction is completed by abstraction of the product from the carbon, that is bearing electrophile, by anionic species Y-, which is present in the reaction mixture and forms a substituted product. Thus, applying the general mechanism on nitration, this general mechanism is applied for nitration, hallucination, sulfonation, Friedel-Crafts alkylation, and acylation. So this is applied, and previous class I have discussed about the nitration and the hallucination. Now today's class I'm going to discuss about sulfonation, alkylation, and the acylation reactions. Sulfonation reaction is generally carried out by using sulfuric acid with excess of sulfur trioxide, though it is itself formed in the first step from sulfuric acid. It acts as the electrophile and it acts as the benzene ring formation, forming the carbocation in the second step. third step is it loses the protons to form anion, and this on protonation in the last step forms benzene sulfonic acid. So sulfonation we do with the sulfuric acid, excess of sulfur trioxide is generated. It is a neutral electrophile. Electrophile is generally positively charged, but the sulfur trioxide is neutral electrophile. So generation is the first step. So general steps involved in this electrophilic substitution explain. Now taking the example of sulfonation, once again we'll discuss the three steps. The sulfur trioxide acts as the electrophile. It attacks the benzene ring, forms a carbocation in the second step. And in the third step, it loses proton to form anion. And the substitution in the last step forms benzene sulfonic acid. Your benzene get the sulfur trioxide neutral electrophile by taking excess of sulfuric acid. Here, from this, get the the sulfur trioxide electrophile and benzene sulfonic acid is formed. We'll see the mechanism. 2H2SO4 reversibly gives H3O plus HSO4 minus plus SO3 minus. In the step 2, what happens is the carbocation is generated. Benzene, sulfur trioxide, plus pi electrons are shifted to the oxygen, sulfur gets the positive charge. And the positively charged sulfur attacks onto the benzene carbon. If the pi electrons are shifted to this carbon, carbon gets negative charge and the sulfur gets the positive charge. So this S plus is attacking this carbon. Here, this is the carbon plus formation and SO3 minus formation. Next, in the third step, here this is the benzene, here it's formed. And these electrons, here you can see this is the ring, and now this is the benzene ring, sulfur trioxide has attacked, and HSO4, presence of HSO4 minus. These electrons are shifting to this carbon. Carbon gets a negative charge. Finally, sulfur trioxide minus is formed. And this one on reaction with H3O plus, you get SO3H, benzene sulfuric acid. And in step 2, you are getting carbocation. Here, the resonance structures are not shown, but I'm going to explain you how it's formed. So step 1, sulfur trioxide is formed. Sulfur trioxide is attacking benzene. The pi electron shift towards the carbon. Carbon gets the minus charge and this carbon gets the plus charge. Where the carbon is getting minus charge, the sulfur plus attacks. And the sulfur, after attacking, carbocation is formed. This carbocation, whatever carbocation is formed, it is shifting from ortho to para and to ortho positions. How it's shifting is the pi electron shift towards the positive charge. Here this carbon gets the negative charge and plus minus forms a bond. This carbon gets the positive. So plus is shifted from carbon, ortho carbon to the para carbon. This is second resonance structure. And in the third resonance structure, what happens is now the positive charge is in the para position. The pi electrons shift here. Here you are getting the pi and this pi bond is completely gone. You are having a positive. Now, those pi electrons shift towards the positive charge. So here you get the negative charge and this is the positive charge, and between these two you get the bond. Get the bond. And this carbon you'll be getting the positive charge, orthocarbon. So the positive charge is shifted from orthocarbon, again paracarbon, again orthocarbon. So finally, the three resonance structures are formed and resonance hybrid is formed. Resonance hybrid is formed. And after that, this resonance hybrid, it is getting stabilized by the resonance structures. And finally, one of the carbocation structure you can take, the H plus hydrogen will give the electrons, and thereby the positive charge is gone. The carbon, benzene, you can see the double bond is formed again, and sulfur trioxide. And this sulfur trioxide on reaction with H3O plus, you get benzene sulfuric acid plus water. This is the way sulfonation takes place. Now we'll see mechanisms of sulfonation. It is brought about by action of sulfuric acid containing excess of oleum sulfur dioxide. The reaction mechanism it has followed by electrophile. Electrophile is a free sulfur dioxide which is present in the oleum concentrated sulfuric acid and sulfur dioxide. Or it can even be formed by dissociation of sulfuric acid. 2 moles of sulfuric acid. So the electrophilic character of SO3 is due to the presence of electron deficient. It is due to the presence of the electron deficient sulfur atom. You can see obviously in the structure. Thereby the carbocation is formed. Transfer of proton from resonance hybrid stabilizes the sulfonic acid anion. And reaction between sulfonic acid anion and hydronium ion forms the final product. Now we'll see Friedel-Crafts alkylation reaction. Friedel-Crafts alkylation. This reaction involves the action of alkyl halide on aromatic compound in presence of anhydrous aluminum chloride catalyst. The reaction mechanism involves following steps: generation of electrophile and again the same formation of carbocation, formation of the carbocation, and transfer of proton from carbocation to form the final product. And the evidence for the support of the electrophilic character of substitution can be by different factors. Now, the Friedel-Crafts alkylation, a complex is formed between the alkyl group and the Lewis acid AlCl3. The alkyl group is then directly transferred without its pair of electrons to benzene ring. It forms carbocation in the second step. So in the Friedel-Crafts alkylation, a complex is formed between alkyl group and Lewis acid AlCl3. Reaction involves action of alkyl halide on aromatic compound in presence of anhydrous aluminum chloride catalyst. Again, the steps are the same: formation of electrophile and then attack of the electrophile, formation of the carbocation, and the third one is stabilization of the carbocation by the resonance structures. And the last one is the formation of product. Benzene on reaction with methyl chloride in presence of Lewis acid, aluminum chloride, methyl benzene is formed. It's called as toluene. Step 1, electrophile formation. CH3Cl plus AlCl3 gives rise to CH3 plus AlCl4 minus. And the second step is electrophile attacks on the benzene ring. CH3 plus comes here and the pi electrons shift towards one carbon, getting the carbon negative charge. This carbon gets positive charge. The negatively charged carbon is attached to the electrophile methyl group. And this methyl group, AlCl4 minus is formed. And on the benzene ring, you get the positive charge. And this positive charge, whatever is formed, it is shifting whole ring and gets stabilized. The positive charge is shifting from ortho position to para position and again to the ortho position. So, from ortho position, how the positive charge is shifting, we'll see. The pi bonded electrons shift towards the positive charge. This carbon gets the negative charge. The negative charge and the positive charge will form a pi bond here. This pi bond is broken here. This carbon gets the positive charge. So you can notice the resonance bond structure. The positive charge is shifted from ortho to para position. Now, the third resonance structure. The positive charge is at para position. The pi electrons shift towards the positive charge, this para position. This carbon gets negative charge, this carbon gets positive charge. The bond is broken. And the negative charge, positive charge in between, you get a bond. So the pi bond is shifted from this position to this position. Thereby, the positive charge is shifted towards the ortho position. This is the third resonance structure. And sigma complex or the aronium ion or the carbocation or the pentadienyl cation is formed. Okay, so this is the way the carbocation is getting stabilized by resonance structures. And final step is product formation. Now, in presence of this catalyst, the H plus ion gives its electrons to the efficient carbocation and it is flushed as H. So H and Cl forms HCl. AlCl3 is liberated and CH3 is attached onto the toluene, methyl benzene. So this is the way a proton transfers from carbocation to form the final product. Now we'll see Friedel-Crafts acylation. Benzene reacts with acid chloride in presence of AlCl3 forms a ketone. The electrophile is the acylium ion. Alkyl is the R group. COR is the acyl group. So acyl, this you are having the electrophile is the acylium ion, which is generated by reaction of AlCl3 and acid chloride. The acylium ion reacts with benzene in step 2 to form benzonium ion. So if R group is attached, is an alkylation, and if COR is attached, then that is acylation. Benzene, when reacted with acid chloride in presence of AlCl3, forms the ketone. The electrophile is acylium ion and it's generated by the reaction of AlCl3 and acid chloride. Now, acylium ion reacts with benzene in step 2 to form benzonium ion. And in the last step, it is the same removal of proton. It leads to the formation of acetophenone. Okay. Acyl benzene is formed. The example is benzene on reaction with acetyl chloride. It reacts with the acetyl chloride and in presence of AlCl3, this acetyl group is attached to the benzene, acetyl benzene called as acetophenone. It is formed and the catalyst is AlCl3 and HCl is the byproduct formed. So we'll see the mechanism of the reaction. Again, the mechanism is followed in three ways. First one is formation of the electrophile. Electrophile is generated, COCH3 plus is generated, electrophile. And second step here is electrophile, CH3COCl. It reacts with AlCl3 and CH3CO plus is formed and AlCl4 is formed. The first step, carbocation formation, we can see. And step 2, pi electrons shift towards the back carbon. It gets minus charge. And this carbon gets positive charge. And for the minus carbon, minus charged carbon, carbanion, the acetyl carbocation is attached. Thereby, carbocation is formed. Again, the same step, the carbocation is stabilized by its resonance structure. The positive charge on the carbon, it is shifting from ortho position to para position to ortho position. So, in the benzene ring, the positive charge, the carbocation, is getting stabilized by the resonance structures. When the electrophile CH3CO is approaching, benzene undergoes the electromeric effect, which results one carbon atom of the benzene ring gets positively charged and the other one gets a negative charge. Electrophile is attached to the negative charge center, formation of the aronium carbonium cation sigma complex and pentadiene cation. So carbonium ion 1 is stabilized by resonance structure, as I've told you. Structure 1, structure 2, structure 3 and structure 4 will be formed. See, the electron shift to this carbon, it gets negative charge. This carbon gets positive charge. The negative charge and positive charge will form another bond. Now the positive is shifted to the para position. And again, this electron shift to the positive charge. Here this carbon gets negative charge. This carbon gets positive charge at the para position, at the ortho position. And this, both of them, you get a bond. Here the positive, previous positive charge and the newly formed negative charge gives one more bond over here. And this carbon gets the positive charge. So the carbocation is shifting from ortho, para to ortho positions. So different resonance structures are formed. Different resonance structures 1, 2, 3 are formed, as we have discussed previously earlierly, in nitration, sulfonation, halogenation, alkylation. The same takes place even for the acylation. So therefore, due to these resonance structures, it is getting completely stabilized, the carbocation of the benzene, after attachment of the electrophile. It's getting stabilized. And finally, the product is formed. How the product is formed is one of the sigma complex aronium ion or pentadienyl cation. The H plus ion loses the electron and gives to the carbon positive charge. and thereby it gets the deficiency is lost and it gets the bond over here. And AlCl3 is formed and HCl is formed. Yeah, this is the way the final product is formed. So you have some limitations for these reactions. Friedel-Crafts reaction does not have few limitations such as aryl vinyl halides are used as they don't form carbocation easily. Lewis acid often forms complex with aryl amines, making them very unreactive. Polysubstitution occurs in case of alkylation reactions. And presence of electron withdrawing group inhibits the reaction. It inhibits the reaction. And possibility of rearrangement of carbocation takes place to more stable carbocation. So the few limitations. They do not form carbocation, aryl vinyl halides. In the Lewis acid often forms complex with amines, making them unreactive. So the substitution becomes difficult here. And for polysubstitution, in case of the alkylation reaction, you can see polysubstitution takes place for alkylation sometimes. And if electron withdrawing group inhibits this reaction, presence of electron withdrawing group will, if there is any electron withdrawing group, the substitution reaction is getting inhibited. And possibility of rearrangement of carbocation takes place to a more stable carbocation. Acylation can be used only to give ketones. And possibility of rearrangement of alkyl group to give different products than the desired one. So even that is a limitation. There is a possibility of rearrangement for the alkyl group and a different product is formed instead of the electrophilic substituted group. So acylation, it can give ketones and there is sometimes rearrangement of the alkyl groups in alkylation and there is a possibility of rearrangement of the carbocations, more stable carbocations. So these are the limitations. And one more thing, how can you detect the electrophilic substitutions? What is the evidence in support of the electrophilic character of the substitution? Electrophilic nature of the aromatic substitution reactions can be proved by different reactions. See, if substitutions are accomplished by reagents containing preformed electrophilic species. For example, benzene can easily be nitrated by salts like nitronium nitrate, nitronium perchlorate, indicating NO2 plus is an electrophile and real nitrating agent. Yeah, that is one evidence. In Friedel-Crafts alkylation reactions, rearranged alkyl groups are found to be present in substituted product. And Friedel-Crafts reaction of benzene, N-propyl chloride gives isopropyl benzene, but it doesn't give N-propyl benzene. So N-propyl, yeah, benzene on reaction with N-propyl chloride gives isopropyl benzene. Benzene with N-propyl chloride gives isopropyl benzene, but it doesn't give N-propyl benzene. So this can be explained on the basis of formation of N-propyl cation, rearranges for stable isopropyl cation, which attacks on benzene forming isopropyl benzene. So this reaction is the best example for the evidence of the electrophilic substitution. And for the two-step mechanism also you have evidences. One-step mechanism, two-step mechanism also we can see evidences. However, all the electrophilic aromatic substitution reactions proceed two steps, and that has been proved by isotope tracer technique. All the electrophilic aromatic substitutions proceed via two steps, and it has been proved by isotope tracer technique. Benzene was labeled with deuterium and it was nitrated and rate of nitration was determined. It was observed that the rate of nitration of deuterated benzene and ordinary benzene was almost the same. Hence, we can conclude that there is no isotopic effect in aromatic substitution. So now, since a carbon deuterium bond is broken more slowly than carbon hydrogen bond, so the same rate of nitration can be explained on the basis of two-step mechanism. In two-step mechanism, also rate determining step first step does not involve any cleavage of CH or CD bonds. So what I can conclude is absence of isotopic effect established the two-step mechanism for electrophilic aromatic substitution reactions, in which formation of carbonium ion first step, and that is the rate determining step. So absence of isotopic effect establishes two-step mechanism for electrophilic aromatic substitution reaction. And it is in the formation of the carbonium ion is the first step, which is the rate determining step. So the evidences are also discussed. We have seen different ESR reactions of benzene. The first one is the nitration. The second one is the halogenation. So benzene, as we have seen, it is the rich source of the pi electrons, can be easily shared. So benzene is susceptible for the electrophilic attack, both the carbonium, forming the carbonium intermediate ion. Okay, it loses the protons, and different reactions, electrophilic substitutions are there for benzene. Nitration reaction, halogenation, that chlorination and bromination. The third one is the sulfonation. The fourth one is the Friedel-Crafts alkylation. And the fifth one is the Friedel-Crafts acylation. So I hope everybody have understood the ESR reactions of benzene. Thank you for listening to my class. Thank you one and all.